nicotine advertisement. So this is again named after Caesar, but then years later there came along another fellow named Vigenère who actually built upon this idea of a rotational cipher, but didn't just use one secret. Right? A recurring theme you'll see even in computer science is if, well, the first attempt at doing something isn't quite good enough or quite secure enough, maybe do it again, or do it again and try to increase the computational complexity of something. And so what this fellow proposed, the so-called Vigenère cipher, is simply a cipher where you don't use one key, you use maybe 2 keys, or 3 keys, or even 4, and then you use the first key on the first letter, the second key on the second letter, third on the third, fourth on the fourth, and then if your input, your plain text, has 5 letters, then you just repeat back to the first letter in your key. Now, it's a little tedious to remember multiple numbers, like the number 2 and 3 and 13 and 14. And so what Vigenère proposed is that rather than just remember a number, like you might for the Caesar cipher, you instead remember a word. Like my keyword might be A, B, C. And then you simply decide, sort of as a society, that anytime a keyword has the letter A, this is going to represent the number 0. The letter B is going to represent the number 1. The letter C is going to represent the number 2, and so forth. So if your secret, not key, but secret keyword is ABC, that's really like saying we have 3 keys, and they are 0, 1, 2. And so if you want to encrypt something like hello, you can do, if this is the plain text, HELLO, and I want to encrypt it with A, B, C, well, it's 5 letters, so I actually have to repeat my keyword. So I just do this. And now H plus A, well, A is 0, so H plus 0 is H. E plus B is actually E plus 1, so that goes to F. L plus 2, so L, M, N, so that's N, N. And then I'm back to B here. So O, rotated by 1 place, is P. And so, oh, did I mess up? O, L, oh, yes, 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 thank you. This is plus 0, thank you. Bug in the code. All right, so that's L, L. No, 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 hang on. You don't have 300 people staring at you. OK, so plus 2, L, M, N. OK. OK, thank you. We really set the bar high here in 50. OK. So that would now be the ciphertext, right? And now this is actually harder to decrypt or to crack in the sense of trying to brute force your way through it. When we say brute force, it means try all possible keys to figure out what it is. But now this is getting increasingly computational complex. Whereas the complexity of the Caesar cipher, if you're just rotating by a letter of the English alphabet, you have 26 possible keys, really 0 through 25 or 1 through 26, depending on where you want to start counting. How many do you actually have in the Vigenère cipher? Well, for your first keyword, you have what? 26 possibilities. Your second letter in the keyword, you have another 26, and then another 26 possibilities, and then another. So in general, the complexity of the Vigenère cipher is going to be 26 raised to some power, where that power, let's call it k or whatever, is simply the length of that key. So 26 times 26 times 26 times 26. Now this is starting to actually get pretty big. If we use a, let's say, 5-letter keyword alone, let me just pull up a little text-based calculator here. And if I do 26 raised to the 5 power and hit enter, so that's already some 11 million possible keywords that the bad guy might actually have to try in order to figure out what keyword was actually used. Now, here, too, we have computers. And computers can churn through 11 million possible keywords pretty darn fast. Thankfully, though, there exist some more sophisticated algorithms out there, but that's something we'll revisit before long. Now, just as a teaser, for those of you who might be a little shy of tackling the Hacker Edition, realize that this week's is actually pretty open-ended. What we've given you, if you choose to elect this edition, is a password file. So on most any Unix or Linux or Mac OS system, there's a text file historically that contains all the usernames who are authorized to use that computer, and then all of their passwords separated by a colon. So for instance, Caesar, colon, and then his encrypted password, Chartier, colon, and then his encrypted password, and so forth. So these are not in plain text. These are the ciphertexts. And so the challenge of the Hacker Edition this week, if you've not yet dived in, is to take this as input and figure it out. What are each of these people's passwords? And you will find that they are varying levels of difficulties. Rob's is not so difficult. Malin's is actually pretty difficult. And so you'll see that various heuristics are actually applicable here, right? If you were implementing a password cracking program, even if at first glance you have no idea how to do this in C, what kinds of words or what kinds of passwords might you try if the goal is to brute force figure out whose password is what? So you can use what's called a dictionary attack. So this is actually a pretty sophisticated approach. But it turns out in the appliance, as on most computers these days, there's a huge text file with like 150,000 English words. Well, that's actually not all that much to a computer. What you could try doing is open that dictionary file, read through it top to bottom, left to right, and try encrypting every one of those English dictionary words. And if you see a match in this file, as we discussed last week, voila, you figured out what Rob's password is. So in other words, you can't really decrypt these things because they're what we called one-way hashes. But you can encrypt a guess and see if it matches what's actually in this file. Now, other things you might try, honestly, you could try some easy ones. Maybe it's all numbers. Maybe it's the word password. Maybe it's the number 1, 2, 3, 4, 5. So one of the challenges of the Hacker Edition is that because there's actually a whole lot of possible passwords that any one of these peoples could be, turns out that your program could take days, weeks to actually run. So you're never actually going to see, certainly before the deadline, if you're right. And so one of the challenges is going to be write a password cracking program that optimizes for what hopefully normal people might use as passwords, and then only eventually resorts to just trying all possible letters in the ASCII character set, all 256 possibilities. So do feel free to dive in. And even if you decide, I have to abort this particular edition, that's fine. You can then dive into the standard edition. You can choose week to week which one to do. All right. Any questions on p-sets or otherwise? No? All right. So let's go ahead and open up a blank file here. So let me close IUnlock. And recall that we spent some time with this fellow here last week. This notion of 100 bottles of beer on the wall and singing something very familiar to him. Had I actually planned ahead, it wouldn't have been a donut. It would have been a bottle of beer. But that's the first thing that came up on Google. So the connection here is to 100 bottles of beer on the wall. And recall that we implemented this with a lot of printfs and with a main function. But then we started factoring this thing out, some of that code out. So if I recall, we started with something like this. Let me zoom in and do include standard io.h. And that gives me, quick sanity check, what function? Printf, that's all. And now another quick sanity check. Why is it black and white? Where's my color? OK, all right. So we'll notch things up a bit now. That was too easy. All right. So let me go ahead and save this as, let's call it what we did before, beer1.c. Now that gedit knows that this is a C file, it starts syntax highlighting it for us. And then recall how we began this thing. We had int main. I didn't take any so-called command line arguments. Instead, I simply asked the user, how many bottles of beer will there be? And then a question mark. And then I'll put a new line character, semicolon. And now I actually need to get the input from the user. So the function we keep using for this is, OK, so let's call it getInt. OK, feel free to yell at me if I'm making mistakes. This time, that was unintentional. OK, so a couple mistakes already, right? So first, I do need the CS50 library so that I even have access to getInt. And there's still a bug in here already. This won't compile. Yeah? I'm sorry? On the third line here, we need to actually do int, right? So we actually need to declare this variable. And let me see if I can, let's see, turn on. That's OK. I was going to turn on line numbers, but we'll leave it off for now. All right, so int n getInt. So that's good. And now let's go ahead and forge ahead. So I'm going to go ahead now and say for int I gets, let's say, n. I is greater than equal to 0, and then I minus minus. So in other words, I want some kind of loop that, just like the song, is going to count down from however number of bottles I start with. And then on each iteration, it's going to decrement, decrement, decrement. And it's going to stop once we actually hit 0. And then recall that this song was something along the lines of, I don't know what this is going to be yet, bottles of beer on the wall. And then I'll do a new line in this. And let me just do some quick copy paste so that we don't have to type out all these lines. And now let's just change this. 100 bottles of beer. Take one down, pass it around. So that comes next. So take one down, pass it around. That's pretty easy. And then something, something bottles of beer on the wall. So we're almost there. These question marks are illegitimate. So I should probably plug in a OK, so %d, because we're talking about a decimal integer, like 99, 98, and so forth. So let me go ahead and plug that in now. And now what value do I actually want to plug in here? Because right now, printf can't just take one argument. It has to take two. Yeah, so we want to just plug in I, not n. If I plugged in n, what would the song sing? The same number again and again. It would just say 99, 99, 99. So we do want I, because I is the number that's being decremented on each iteration. So now I want I here. Now I want I here. OK, good, right? There is no actual placeholder there. But down here, I want I as well. OK, exactly. So we don't, even though on each iteration we are decrementing I, realize that within one stanza of this song, we have to say verbally two numbers, both where we started and where we're going to end up. So according to that song, we're supposed to end with 98 bottles of beer on the wall. So I minus 1 will do that. Any objections now to how we're doing this? Some tweaks. I'm sorry? Yeah, so thus far, we're not really enforcing any kind of boundaries on n. In fact, if I don't notice that quite yet, let me go ahead and zoom out. Let me go ahead and open up my terminal window here. And let me go ahead and make beer 1. That's good. So it did compile OK, so that's promising. As an aside, we were asked the other day how I keep clearing the screen. If you want to do that, it's just Control L. It just flushes what you see on the screen. So let me go ahead now and run beer 1. How many bottles of beer will there be? Let's say 99. And unfortunately, this seems to err at least once we, oh, now it's just not scrolling back far enough, but that's OK. This is a bug, right? Minus 1 bottles of beer on the wall. Let's fix that one first, because that's the first one that jumps out. What's the easy fix here? Yeah, so it should really be greater than 0, or you could say greater than or equal to 1. Either way would be perfectly legitimate, whatever seems most logical to you. So that should fix that bug, but there's this other one. Let me zoom in again. Let me go ahead and run beer 1. And now let's just be difficult, -3. OK, so didn't sing anything. So that actually worked OK, but why? What caught that error? Yeah, so right, because we're initializing I to -3, and then we're checking that condition, only do the following, so long as I is greater than or equal to 1, well, we're detecting this and effectively not executing any of those 4 printf lines, so we simply quit. However, it's not really clear to the user what's going on, so it would not be unreasonable to say something like, well, if n is less than, let's say, 1, then let's go ahead and say something like printf, please input a positive number. And then that alone could be enough, but generally as a matter of good practice, what should I do after this printf? You probably want to return something other than 0. Again, this is something you sort of should take on faith for now. You don't really see these numbers just yet, but we soon will. But you want to return something other than 0, because 0 generally denotes good, and anything else denotes bad. Now, what about this? I seem to be missing return. So do I strictly need something at the bottom? You don't really, but once your programs start getting more sophisticated, it's not a bad habit to just explicitly return 0. But what C does for you these days is if you omit it from main specifically, 0 gets returned automatically. So that's why we've done that thus far. All right, so not bad. Any questions on this thus far? Why can't you use %i? Oh, so you actually can. I think. I actually never really used %i. I think they're synonymous. But I'll double check. Other questions? All right, so let's now, rather than dump